this video, I would like to work one basic but super instructive example introducing us to series, which are very related to our study of sequences. Now, what I'd like to use as a motivating example throughout this whole video is a unit square. So let's imagine that the length of each side is 1 unit, whatever unit you'd prefer. And as we move from left to right, let's imagine we're in various stages of a process. So this is stage 1, stage 2, stage 3, etc. I'd like to denote by A sub n the area of the newly added shaded region. So let's just animate that for a moment. Here is A sub 1. It's that purely gray portion. Unlike in some geometry problems, I do mean for these pictures to be helpful. So it looks like the length of this rectangle is 1/2, and in fact it is, and the height is that of the full unit square. So this rectangle has area 1/2 times 1, and so that is the first term in the sequence that I'm currently considering, 1/2. In stage 2, I'm only talking about the newly added area. That newly added area has length 1/2 and height 1/2, so all in all that new area is 1/4, and we write that down in our table. And we continue in this way, looking at the newly added area and computing what that is based on successive halving of either the length or the height. So we get this sequence, 1/2, 1/4, 1/8, 1/16, all the way down and so on. And then what I'd like to do is add another sequence into the mix. While A sub n was denoting our newly added area, another thing that might have been of interest to us is the total area. So for now, let's let S sub n denote total area, and let's do the same process to see if we can come up with a formula for what S sub n is. At stage 1, both A sub n and S sub n are exactly the same, and they're 1/2, but at stage 2, we start to notice a difference. Our newly added area was 1/4, but we need to add that to the previous area that we had, so the answer for S sub 2 would be 1/2 plus 1/4. Now I'm perfectly capable of simplifying that fraction, but remember that when we're dealing with sequences and with series, we do not simplify because we like to leave things expanded in order to see a pattern. At stage 3, my newly added area is 1/8, and I need to add that to the two other areas that I have, which are 1/4 and 1/2. And we can continue in this way, but our sums start to get very long and make us run off the page. So for now, I'll put ... for stages 4 and 5. And then let's take a look at stage 6 to notice a pattern. At each stage, what I'm doing is taking the term that I have, my new area, and I'm adding that to the area that I had in the previous stage. And something that denotes all the area that I had in the previous stage would be the one before it. So at each stage, the entry that should go right here, for example, would be the sum of my newly added region to the previous total area. Newly added region, previous total area. Newly added region, previous total area. Now I'd like to make an aside. Notice that on the previous page we had an issue with writing out this long string of sums. It was starting to take up space, and if we were writing by hand, it would be a very annoying process to write 1/2 plus 1/4 plus 1/8 plus 1/16. That would be a lot of writing to do. Just like we did with factorials, when expressions start to go on and on and on, but there's a pattern, we use an abbreviation. Now the abbreviation that we use here is a big capital sigma, and sigma is the Greek letter for S, and that S is standing for sum. So this big old sigma is saying I want to sum things, and what do I want to sum? I need to tell a sum where to start and where to stop, and then I need to say the things that I am summing or adding. So for example, if I wanted to add 1 plus 2 plus 3 plus 4 plus 5, I would say that I would like to sum starting at stage 1 and ending at stage 5, things that just have the form I. So when I is 1, we get the 1. the sigma stands for sum, then I moves on to become 2, and 2 is the term that I put right here, and then I put a plus sign for the sum, and so on, and I stop when I've reached 5. And even though here I was adding 1 plus 2 plus 3 plus 4 plus 5, there was nothing saying that I really needed to start at 1. If I only wanted to count 3, 4, 5, I could just indicate that by having a start value here 3 instead of a start value at 1. So if we return to our example, when we were writing things like 1/2 plus 1/4 plus 1/8, we could have generally recognized that this term has the form 1/2 raised to a particular power, and we could have said I'm adding 3 terms, 1, 2, 3, of the form 1/2 to the I. I being 1 gives me a half, 2 gives me a fourth, and 3 gives me a 1/8. So that S sub n term that we didn't write out because it would have been too long in stages 4 and 5 and 6 could be defined using this very fancy sigma notation as the sum as I goes from 1 to n of 1/2 to the I. It's a little tricky because we have 2 variables. The I is what's sometimes called an iterator, and it's passing through these different values. It starts at the beginning, a very good place to start, and stops at this particular n value. Now where this comes into us is that the next topic of study for us will be what are called infinite series. They are the sum starting at 1 and this time going all the way up to infinity of some terms, where the a sub n terms, or the addends, can be written according to a particular pattern or rule. Now we can't actually add to infinity, and so the way that we define this infinite sum is as a limit. And it's a limit of what are called nth partial sums, which are the things we called S sub n before. So S sub n starts at 1, stops at n, so is a finite sum of the first n terms. Returning to our example, here is n, 1, 2, 3, 4, 5, 6, and then we could continue on to a general term. We already saw that our addends had the form a half, fourth, eighth, in general, 1/2 to the nth power. And our S sub n's, where I had 1/2, 1/2 plus a fourth. Previously, I had a half plus a fourth plus an eighth, but I could simplify that to 7/8. So one way to obtain these values is to actually do the sum, 1/2 plus 1/4 plus 1/8, find a common denominator and do that sum. Because we chose a motivating example where we had a visual, we could return to our visual and we could find these sums from a subtractive principle as well. We know that the total area of the square is 1, and we're interested in the gray area. One way to find that would be to compute the total area minus the white area, which is 1 minus a fourth for this example, or 3/4. 1 minus an eighth for this example, 7/8. 1 minus 1/16, or 15/16 for this example. So either by finding a common denominator and adding, or by returning to our visual example and using a subtractive principle, either way, we're able to come up with a pattern for the nth partial sum of our sequence, and we're able to either use limit techniques and end behavior models in calculus, or use our intuition in our visual example to say that as these stages progress further and further, the gray area is getting closer and closer to the total area of this unit square, and therefore the value of this infinite series, the sum of terms of the form 1/2 to the nth power, as I goes from 1 to infinity, should be 1. We'll be studying infinite series for a long time, and it's always nice when our infinite series relate to examples we've seen in life before, especially in the beginning as we're just learning, and so that's where we'll be going next.